Maybe I'll just wait for 1 or 2 more minutes. All right. All right. Yeah. All right. So we have more than 50 participants currently. So I don't. That's a big number. So we can just start. So hello everyone. Uh, Good afternoon. I'm Sowgat Muzahid, and I'll be talking about probing the dark baryons in the universe. I don't know whether you can see my cursor. Can someone confirm? Just unmute yourself and talk to me. Anyone? I see chats. Okay, you can. Very good. Right. So, yeah. The title of today's talk is Probing the Dark Baryons in the Universe. Okay, and as you know, the baryons, by baryons, I mean ordinary matter. And by dark, I mean those baryons do not emit. Okay, and therefore, it's not possible to directly detect them. And the purpose of this talk is to sort of give you some flavor of the type of work that we are doing at IUCAA. And there is quite a few people at IUCAA who are working on a similar theme. Myself, Professor Raghunath Sri Anand, Professor Neeraj Gupta, and their students and postdoc. And I, I should emphasize that the team we have, if you see worldwide, actually, we have, I think, one of the sort of major groups in the world working on this field. You take any other places in the world, you don't find so many people working on the this topic. So that's good news. So in this talk, I'll try to basically tell you people what we are doing and why we're doing. Mm. So let's start with okay, this mass energy density budget of the universe. I think you have already seen this kind of plot or pie chart from your introductory cosmology lecture, that today's universe is thought to be composed of dark energy, dark matter, and baryons, right? And this pie chart shows their contribution to the total mass energy density. And you can see that vast majority of it is actually dark energy. It's 70% of it. And then dark matter is only about 27%. And ordinary matter uh, is basically the baryons. They are only about 5%, right? The dark matter, dark energy, it drives the accelerated expansion of the universe. So it's repulsive in nature. Whereas dark matter holds the cosmic structure together. It acts like a glue, or you can think of cement when you are building a multi-storied structure. Okay, and the baryons, that's basically what we see with our eyes or with the telescopes. The awkward situation in this scenario is that the dark components, both the dark matter and dark energy, they do not interact with electromagnetic field, and therefore they remain undetected. Okay, although there are indirect evidence of their presence, but we cannot directly confirm those components. So the ordinary matter, which is only of 5% of the total mass energy density budget of the universe, is what we see. Okay. So today's talk, I'll tell you that even this 5% of ordinary matter, not all of it can be detected. Okay. We'll see that almost 30 to 50% of them are not even accounted for, which means at low redshift, we don't know where they are. And that's equally awkward situation. So let's take this example from the Eagle project. So that's a simulation. It's a sort of gas density distribution in a cosmological simulation. So what cosmological simulation basically do is to sort of mimic the way universe might have evolved using different input physics and see what different observables and how they compare with sort of observations. Okay. And although the exact nature of the dark energy and dark matter components we don't know, yet cosmological simulations are remarkably successful to reproduce the large scale structure. So you see that this is large scale structure reproduced by Eagle simulation. And here different color indicates different gas phases. Okay. So for example, you see the blue color, if you can still see my cursor, it's filling most of the volume. You can see everywhere blue color, right? So that represents gas with temperature few times 10 to 4 Kelvin. Okay, and then there is this green color on top of the blue. It actually represents warm hot gas, which has a temperature of 10 to 5 to 10 to 6 Kelvin. Okay, and you see that the very high density region where lots of cosmic filaments meets. We call them nodes. Okay, so in different nodes, you see that there are hot gas and a red color here basically shows the map of hot gas. So hot gas meaning temperature more than 10 to 6 Kelvin or so. Now the catch here is that the cool and warm hot gas with temperature, let's say 10 to 4 Kelvin to 10 to 6 Kelvin. So they are filling most of the volume in the simulation box, but they are not directly visible. Okay, it's because of the simulation you know where gas are, but in real universe you don't see them. Okay, so because of their very low density and density of this media is like 10 to minus 3 particles per cc per cubic centimeter. Okay, so the hot gas, let's consider the hot gas that you see in red. They are also low density, but going to the very high temperature, you can directly detect them. Okay, through emission. For example, X-ray or gigahertz observation, you can directly see them. So, for example, the X-rays, the underlying physical process is thermal bremsstrahlung or free emission. In the case of gigahertz observation, it's basically follows from the fact that there is inverse Compton scattering of CMB photons. Okay, so now let's look at this same patch of the simulation box with stellar light. So let's forget about the cool, warm, hot, and hot gas. If we just see the light coming from the stars, so how this same patch of the universe would look like. So that is shown here. Okay, yeah, you see that with stellar light, you are only seeing the the densest parts of the universe, and most of the sort of volume that were filled by blue and greenish color, that means cool and warm hot gas, you don't see them. Okay, so that's really interesting, and I'd like to emphasize that the like astronomy started with observing stellar light, right? First, we did the observation of the stars in the Milky Way, our own galaxy, and then we went on to probe sort of extragalactic objects. That means galaxies not belong to like beyond the Milky Way. And in all of these cases, like historically, we measured the stellar emission. Okay. But now you see the issue that if we only focus on the stellar light, then we may be missing a whole lot of interesting physics, uh, which you won't be able to detect through stellar light. So, okay, so stellar light is good, but it's not all. Okay. So moving on. So this slide is basically to tell you the reservoirs at which those uh, cool slash or the warm hot gas could reside. Okay, so let's split the universe into two. First of all, galaxies living in high density region of the universe, and then intergalactic medium. It's really far away, and when I say far, it's like megaparsec scale I'm talking about. It's really low density medium. And so galaxies are collapsed objects. They are collapsed under its own gravity, whereas intergalactic medium is cosmologically evolving. And most of the volume of the universe is filled by this diffuse gas in the intergalactic medium. And galaxies, again, someone is requesting remote control of my screen. Why? I should decline that. Okay. And galaxies, you can again uh, uh, divide into three main components. Of course, galaxies are composed of stars, and there are gas in between stars, which we call interstellar medium, which is relatively high density. It's like one particle per cubic centimeter. And there's this halo of gas around galaxies. Um, which has again very low density, 10 to minus 3 particles per cc. Okay, so you see that within these galaxies, we can only observe directly through emission the stars and the ISM, okay, emission line from the interstellar medium. The CGM, circumgalactic medium, again, it's very low density. It is as low as the intergalactic medium, and as such, there is no uh, sort of demarcation line that this is the circumgalactic medium and that's the IGM. It's not there. But the immediate vicinity of ISM or the stars, we call it CGM. So CGM will basically become an intergalactic medium as you go far away from galaxies. Okay, and then galaxies, they can live in fields, meaning there is no companion around them. And one of the classic example is UGC 2885. It's also called Rubin's galaxy, after Vera Rubin, who actually discovered the fact that stars uh, in this particular galaxy, and there are I think about I don't know the exact, I don't remember the exact number of her sample, but in her study, she found that the stars are moving faster for their mass. Okay, and that's basically led to the discovery of dark matter. Anyway, so this is the classic example of isolated galaxy, UGC 2885, where there is no other sort of companion. Okay, and so galaxies can live in fields or in groups. Okay, so where there are multiple galaxies in a relatively small patch of the sky. Here, classic example is Stephen's quintet. Okay, you see 1, 2, 3, 4, and 5. There are 5 galaxies very close by, and and there is this medium in between these galaxies called intergroup medium. So it's IGRM, or intergroup medium. Or the extreme examples are the clusters. For example, I'm showing you a HST image of Abel 1689. So where you can see hundreds of galaxies in a very small patch of the sky. We call them clusters. Okay, again, this is also a collapse object, the entire structure. And then there are gas in between these galaxies, what is known as intercluster medium. So if you want to do a census of baryons, then you have to sort of calculate how much baryon resides in the intercluster medium, how much baryon is residing within the intergroup medium, or in the circumgalactic medium of isolated galaxies, and in the intergalactic medium. Okay, then it will get the entire picture. So so I see some question that why not infrared imaging? Won't it be better for heat maps? Yeah, you can do infrared imaging, but uh, I don't know what do you mean by heat map. Mm. They don't trace the temperature that I'm talking about, like 10 to 4 or 10 to 6 Kelvin. No. Okay. And medium, what do you mean by medium? So so medium is medium, right? It's like, let's say you have one galaxy and there is another galaxy, and it's not empty in between. Okay, so anything in between, you call it's a medium, right? Okay, and so I was talking about the baryon sensors, and you can see uh, that people have already done that. For example, Mike Shull in 2012, in his ABSIP paper, he presented this pie chart of the 5% of the universe's mass energy budget, and where are those like 5% of those. Okay, so this is true for redshift less than 0.5, and you see that galaxies, meaning the stellar light inside galaxies, they only contribute 7% of the total baryon. Okay, and then circumgalactic medium, which is halo around individual galaxies, they contribute roughly 5%. So this galaxy's stellar light is directly visible through emission. The circumgalactic medium is not. This is again, we'll see how one can probe this contribution of the circumgalactic medium. And there's this ICM, intercluster medium, which is also directly visible through X-ray emission, which contributes only 4%. Okay, and the coal gas in the ISM contributes about 2%. Okay, so coal gas meaning it's like a H121 centimeter emission. So if you add these galaxies plus ICM plus coal gas, it will be 7 plus 4 plus 2. So it's like only about 13%. Okay, so only about 13% baryons are directly visible through emission. You can see, and the remaining baryon is not. So, and moving on, then you see this photoionized Lyman alpha forest. I'll tell you what does that mean. But it's a component or phase of the gas. It's like 10 to a few times 10 to 4 Kelvin gas. They contribute about 28%. And then this warm hot intergalactic medium, which was represented in green in the simulation that I showed, uh, and if it is stressed by Lyman alpha, then it's about only about 14%. And then if it is stressed by oxygen 6, these are bit technical. I may or may not touch upon this, but you can see that warm hot component, that is 10 to 5 to 10 to 6 Kelvin gas, they contribute about 14 plus 70%. Okay, and this 29% or about 30% cases, 30% of the baryon, they are not accounted for. We don't know where they are, right? So two important sort of messages from this slide. One is that 60% of the cosmic baryons do not emit light. Okay, so they are basically dark, and 30% of the cosmic baryons are yet to be detected. So they are also dark. Okay, because you don't even see them, and this is what is known as the missing baryons problem. Okay, and this is a conundrum unsolved for almost 2 decades. uh, we don't know the nature or where are those basically missing baryons. So that's a sort of active field of research, and in IUCAA, we have been also trying to address these questions, which I'll come to. Uh, I'll discuss later. So how do we see this invisible, those baryons that do not emit any light? Excuse me. So for direct detection, baryon must emit electromagnetic radiation, right? Because that's what we observe through telescope. And there are several channels through which gas can emit. For example, inverse Compton cooling, free emission, radiative recombination followed by de-excitation, and collisional excitation followed by de-excitation. All of them can give you emission. And the catch here is that the emission measure is varies as density square, because it's a particle-particle interaction. So let's say you have some ion, then electron is recombining, and then the electron is like making a transition to a lower energy state, or you call it a de-excitation. So in that case, you need the chance of that happening will be depending upon the density of the incident electron and the density of the ion. So emission measure is always density squared. It's although it's not true for inverse Compton scattering, because in this case the CMB photon gets upscattered by thermal electrons. Okay, so but all other sort of atomic processes, emission measure will be proportional to density squared. And therefore, if the density is very low, like 10 to minus 4 particles per cc, 10 to minus 3 particles per cc, then they don't emit much electromagnetic radiation. And in terms of surface brightness, it will be less than 10 to minus 20 arcs per second per centimeter square per arc second square. But the interesting thing is that although they do not emit much, they can absorb electromagnetic radiation. And that's what we will use, that property, that electromagnetic emission going through a very diffuse medium. Even that diffuse medium can absorb the electromagnetic radiation. And in this case, the optical depth for absorption, you write it as tau, then you can, this tau optical depth would be equal to the density of the absorbing medium and the line of sight distance of the absorbing medium and the absorption cross section, sigma. And this n times L, the density times the length of the absorber, is called the column density. Okay, so basically your optical depth is column density times the absorption coefficient. But you see that the optical depth for absorption is only proportional to n, as opposed to emission measure where it's proportional to density squared. Therefore, for diffuse medium, to probe diffuse medium, absorption is always better or more sensitive compared to studies with emission lines. Okay, so we'll do here a little calculation. Let's take sort of cloud with neutral hydrogen, and let's say there is ionizing photon. That means you have incident photons with 13.6 electron volt energy. Okay, so that photon, the ionizing photon, will see a cross section for neutral hydrogen of the order of 6.310 minus 10 to 18 centimeter square. And you can see that this is very close to the Bohr radius square, which may not be very surprising. Okay, and then let's calculate the column density you would require to obtain a unity optical depth. Okay, so in this equation, tau equal to n sigma, you set tau equal to 1, then the column density of neutral hydrogen will be 1 by sigma, right? And that means 1 by this factor, which will be 10 to 17.2 per centimeter square. So basically, if you have a diffuse cloud, which is not emitting much, but it has a column density of a few times 10 to 17 per centimeter square, then your incident continuum or incident radiation will be absorbed by E folding. So if you, in terms of radiative transfer equation, I equal to I naught e to the power minus tau, and tau equal to 1, then it's basically I naught by E. So that means your E folding decrease. Okay. And moving on. So how do we sort of see this invisible gas? Okay, and that's what we have been discussing, and we already sort of seen that we have seen that absorption line is, or your diffuse gas absorption line technique is more sensitive to probe a diffuse gas, and this figure is basically give you the experimental setup. Okay, so what we do is we observe very bright source, usually a quasar. Okay, you can see them really quite far away from you. They're really bright. They're brightest object in the sky, extragalactic object. And then you see that there is this diffuse gas clouds. Okay, here, and let's for example assume that they are only composed of neutral hydrogen. Okay, so then this cloud will absorb the photon at Lyman alpha, which is like 12-15 angstrom, but the absorption signature won't be at 12-15 angstrom because it's far away from us, and this absorption feature will be redshifted. Okay, so if it is at redshifted by 1 plus z factor. Okay, so you can see that this cloud will produce an absorption signature in the red part, and the cloud that is somewhat nearer to us will produce another absorption feature somewhat bluer compared to the this cloud. Okay, and the cloud which is very close to us will again produce absorption feature bluer of the second cloud. Okay, so further the cloud, so their signature will be more redshift. So the final spectrum of the quasar would look like this. So there is this continuum of emission, so which is shown in the red, in the blue, green, and this color pattern. And on top of that, you see absorption lines, right? So we'll basically study those absorption lines to see what is happening in this gas clouds. So that's sort of, now let me see. Yeah, okay. Can you, yeah, so it's basically, it's a movie that I found in the internet. It's nicely demonstrate how quasar spectrum is actually produced. So that's the quasar really far away from us. Okay, and that's the unabsorbed continuum of the quasar. Okay, you see there are emission lines coming from the quasar. For example, this is Lyman alpha, and Lyman alpha being one of the strongest transitions you see a very strong peak. And there are these peaks from other metal lines such as carbon 4, silicon 4, etc. And let's allow the photon pass through the intervening medium to us. Okay, so you can see as the photons traveling towards you, they are intercepting a gas in between you and the oh, okay, sorry, you and the background source. And let me just stop here, and you can see that something really interesting is about to happen. Okay, so this light is passing through a foreground galaxy, very close to a foreground galaxy. Okay, and let's see what you see. It's just entering the disk of the foreground galaxy, and you see there's a booming absorption. It's very strong absorption when it's going through galaxy disk. And this kind of absorption we call damped Lyman alpha absorption. We'll probably cover that in a bit. So, and not only that, because your galactic disk, they have lots of neutral hydrogen, okay? And that's why you see very strong absorption corresponding to this galaxy. And not only that, it is also giving you lots of super strong metal lines, for example, carbon 4, silicon 2, silicon 4, etc. So this is these absorption lines actually keeps imprint of the metal content, the metallicity, relative abundances, etc. Okay, so let's move on. So every time it is finding any absorbing atom or cloud, it's basically producing some absorption in the spectrum. So the final spectrum will look like something like this. Okay, so we have unabsorbed continuum, and on top of that, lots of absorption lines, which we will basically study to understand the medium in the background quasar and us do not emit much electromagnetic radiation. Okay, so yeah, it's just a sort of not very relevant slide, but we are using astronomical or astrophysical spectroscopy. And to do that, it's just to remind you that you need something which can disperse light into its component wavelengths. And we have this a very mm, mm, common example that we probably played with prisms when we were kid, and they basically can disperse light, right? But since the extragalactic sources are really faint, we cannot use prism as dispersing element, because we lose a lot of light every time it goes through the medium, that is the prism. It also reflects and so on. So basically, it's not very efficient. So we cannot do astronomical spectroscopy with prism, and it also doesn't give you very high resolution. So instead, what we use is, uh, you probably know, the diffraction grating. Okay, so there are two types of diffraction gratings. One is transmission grating and reflection grating, but forget about the details. So just keep in mind that for astronomical spectroscopy, we use gratings. Yeah. So let's go back to the quasar absorption line spectroscopy again. So we saw how basically intervening medium uh, modifies unabsorbed quasar continuum. And you see here I'm showing you two quasars spectra. One is at redshift 0.15, and another is at very high redshift. It's redshift 3.6. And x-axis is the rest frame wavelength, or uh, the wavelength at the rest frame of the quasar, and y-axis is intensity in some arbitrary unit. you can see clearly that the spectrum of the low redshift quasar is very different compared to the spectrum of the high redshift quasar, right? You can see lots of absorption, what we call Lyman alpha forest, uh, blue word of the Lyman alpha emission from the quasar, whereas you see very few absorption lines, Lyman alpha absorption lines in the low redshift quasar. And you can see that they contain so much information, even without doing anything. You can see a stark difference between these two. And this has something to do with the physical condition in the intergalactic medium of high redshift and low redshift universe. So that's really, really fascinating. And two other important aspects of quasar absorption line spectroscopy is that it probes the medium in a luminosity unbiased way. So whenever you want to see something in emission, your tendency would be to focus your telescope to the brightest object, okay, because the fainter objects will take you longer exposure time, and that's not sort of easy to get a whole lot of observing time with state of the art telescope. So whenever you do your like emission line studies, they will be inherently biased towards the brightest object. But here, the absorbing medium, it doesn't really matter how bright is the absorbing medium, because we are considering only the absorption caused by the medium. And secondly, this quasar absorption line spectroscopy can probe a wide variety of astrophysical environments. For example, they can probe a medium with densities 10 to minus 5 to 10 to 5 particles per cc, temperatures of 100 Kelvin to 10 to 6 Kelvin, metallicity is very low metallicity like 10 to minus 3 with respect to solar metallicity to 10 times solar metallicity, and line of sight sizes. They can probe sub-parsec scale structure to kiloparsec scale structure. And one of the famous spectroscopist, Blair Savage, who did lots of pioneering work using Hubble Space Telescope, and even before that, using IUE. So he once said that if a picture is worth 10,000 words, then a spectrum is worth 1,000 pictures. Okay, and I can assure you that that's not an exaggeration. They contain really lots of information. Okay, so moving on. Hmm. Okay, so now that you have lots of absorption lines in the spectrum of the background quasar, first thing is to sort of identify the lines. Okay, how do you do that? Because there are all sorts of atomic transitions, and there are this whole range of redshifts between you and the uh, background quasar, and they will all produce some absorption feature in the spectrum. So it's really sort of tricky to sort of identify uh, which absorber or which element from which absorber is causing this absorption. And you see that this is the I'm sure you are familiar with this equation, where your lambda observed equal to lambda rest plus times 1 plus z, where z is the redshift, lambda rest is the rest frame wavelength, and lambda observed is the observed wavelength, right? So you can see that at any given observed wavelength, there can have like multiple transitions, and coming multiple transitions falling in the same observed wavelength, coming from multiple different redshifts. So there is this degeneracy between rest frame wavelength and redshift. Okay, but there is a way. It's not impossible. We do it day in day out. So, for example, we'll use this simple trick that for two known transitions with rest frame wavelength lambda 1 and lambda 2, okay, so lambda 1 rest and lambda 2 rest, so the ratio of the observed wavelength would be equal to ratio of the rest frame wavelength, because they are coming from the same redshift. Okay, so that's what it is. So this is the simple trick will be used. For example, in red, I'm showing you one spectrum. So you see that this is the red spectrum, okay, and you see some absorption line, and a similar pattern is repeated here, okay. And so now what I did is like, I know that there are sort of doublet transition. For example, here it is Mg2 doublet, one having wavelength of 2796 angstrom and another having 2803 angstrom, 2803 angstrom. So as we just said, that the rest frame wavelength ratio will be exactly equal to the observed wavelength ratio. So what I did, I shifted the wavelength array of the original spectrum that is plotted in red by this amount, lambda 1 rest by lambda 2 rest. Okay. And when I did that and I overplotted in blue, so you see that this line now is plotted in blue is falling on top of the red line. So with these kinds of match, we can clearly sort of identify that or tell you that this is magnesium 2 absorption. And now once you identify the absorption, you can now you know where exactly is this line situated, which is roughly at 3998 angstrom in the observed frame. And you know the rest frame wavelength of 20 magnesium 2, the first member of the doublet is 2796. So then again, you use this equation. So you can get the redshift by 3998 divided by the rest frame wavelength minus 1, so which is roughly equal to 0.43. Okay. So then we know that this is an Mg2 absorption arising from a cloud which is having a redshift of 0.43. Now, of course, life is not simple, so you'll have to do it in iterative way, and every time you have to do lots of checks that this is not something else, that is not something else. So and but this is the simple basic principle through which we identify lines and calculate their redshifts, right? And now once you observe identify lines and obtain their redshifts, in order to get the physical conditions of the absorbing gas, you'll have to make some measurements, right? And the easiest thing that you can measure from a spectrum is called equivalent weight. So let's say this is your continuum of quasar continuum, and that's your absorption line. So equivalent weight is basically the area under this profile. Okay, and mathematically you can write is equivalent weight equal to 1 minus I by I naught. That means you're normalizing the flux by the quasar continuum, and d lambda. And d lambda runs from lambda 1 to lambda 2, the wavelength within which your absorption is detected. And if you again use the radiative transfer equation, and this I by I naught is nothing but e to the power minus tau d lambda. And if the line is very weak, or we also sometimes call optically thin, then your tau optical depth is much less than 1. And with that approximation, you can write e to the power minus x is 1 minus x. So if you plug that in, so the equivalent width will be tau lambda d lambda, right? And tau lambda we have already seen that tau is n sigma L, where n times L is the column density, or that means your tau is n times sigma. So here n integral of sigma d lambda. And that you can approximate as column density times sigma 0 times d lambda, where sigma 0 is the mean absorption cross section over the line width delta lambda. So you can see then if the line is weak, then equivalent weight is directly related to column density, right? And then column density also contains the information about density. So uh, probably in this talk we'll not go in that detail how we can obtain density from column density, because that would require some bit of groundwork, background work. So, but you can see that with this equivalent width measurements, you can get the information about density, which is hidden within the column density. Okay, and in the optically thin line, your equivalent width is directly proportional to the column density. Equivalent width is proportional to column density. But even you don't need to do such an approximation. You can, in principle, express this sigma lambda, this absorption cross section, can be written as sigma 0 times phi lambda, where sigma 0 is the line center absorption cross section, and phi lambda is the profile function, which describes this profile. Okay, and this profile function or the broadening function can be we call it profile function or the broadening function, and the sigma 0, the line center absorption cross section, can be written as this, where symbols have their usual meaning, where GU and GL are the statistical weights of the upper and lower atomic level, and AUL is the Einstein A coefficient. So okay, so I'm here rewriting this sigma as sigma 0 times phi lambda, and phi lambda we call it broadening function. And there are processes, three main processes through which a line can be broadened. One is natural broadening, and it follows from the fact that atom or has like finite lifetime of any given atomic state. So you probably have read in quantum mechanics course that delta E times delta T is of the order of h cross, and that's what is gives you the fact that your atomic level has finite lifetime. It actually gives you some uncertainty in the energy measurements, which we call natural broadening. And then second component is thermal broadening, and it follows from the fact that the gas has some finite temperature, and therefore they are moving. They are not at rest. Okay, so that gives you thermal broadening. And finally, there is pressure broadening because of a finite density of the absorbing medium. And this natural broadening and pressure broadening, they have a profile which can be described by Lorentzian, which is shown as this. L is gamma squared by this factor, where x is frequency and gamma is damping coefficient. And in case of thermal broadening, uh, the profile can be explained by a Gaussian profile, which you all know, exponential x minus x0 by 2 sigma squared. So the intrinsic shape of a line would be a convolution of all the processes. That means Lorentzian profile and Gaussian profile. And in this context, we'll call them void profile. Okay, so this V is G convolution and L. Okay, GX and LX. But that's not what we observe. So that's the intrinsic shape of the line. But the intrinsic shape of the line is observed by an instrument which has finite resolution. Okay, and therefore intrinsic shape will be convolved by the LSF. What LSF is line spread function of the instrument. Okay, that's what we'll observe. So in this figure, it's basically showing you the void profiles for different sigma and gamma values. Sigma is the characteristics of Gaussian profile, and gamma damping coefficient is the characteristics of Lorentzian profile. And you can see this red and black. These are the two sort of extreme ends of this thing. In case of black, you see gamma is 0. Okay, so that means black is dominated by Gaussian, and in this case, red its gamma is really high, 1.8. So its core is dominated by Gaussian, and the wing is dominated by the Lorentzian profile. So you can see that in general, Lorentzian profile have stronger wings compared to Gaussian. So So now that we know how absorption line would look like in the spectrum, so we can also do some measurements of the line width. We call it B parameter. It's B squared. You can this is basically equal to square root of 2 sigma. B equal to square root 2 sigma, where sigma is the full width that half max. And this Doppler parameter can be decomposed into thermal and non-thermal components. So thermal is basically, as we said, this uh, it's coming from thermal broadening. So that, and anything that is not thermal, we call it a non-thermal contribution. And B thermal, again, you can write it as square root of 2 kT by m. And now if you plug this Boltzmann's constant here, you can rewrite this equation as 12.8 kilometers per second, square root of T4 by MA, okay, where T4 is the temperature in units of 10 to 4 Kelvin, and MA is the atomic mass. So for example, hydrogen, pure hydrogen at 10 to 4 Kelvin temperature will give you a line width of 12.8 kilometers per second. Okay, so that's all it means. Now, if you have two transitions, like two Doppler parameter measurements from two different elements, okay, let's say with atomic masses of m1 and m2, then you can write this equation for two lines. One would be like b1 squared equal to 2 kt by m1 plus bnt squared, and b2 squared is similarly 2 kt by m2 plus bnt squared. And you see that this is non-thermal contribution is same for uh, both the transition, because they're coming from the same region. And now basically you have two equations and two unknown, right? So you can in principle solve for the non-thermal contribution or turbulence in the medium and the temperature of the absorbing gas, which is really uh, powerful tool. And in case you do not have any other sort of well measured transition, let's say you don't have multiple transitions from coming from multiple like different species, for example hydrogen, carbon, silicon and carbon, even in that case you can see that Doppler parameter measurements can give you an upper limit of temperature. So you can always assume that your entire B parameter is contributed by thermal broadening. Okay, so that means you are assuming B and T equal to 0, and under that approximation you can get an upper limit for the gas temperature, uh, which is also really interesting and important, and we usually use in our analysis when we don't have very transitions available. So what can be the maximum temperature of the gas that is absorbing and producing a transition of your interest? So then, yeah, so okay, let me I think I'll basically have to skip so this part. Okay, I'll just skip. I have only 5 minutes. So let me just briefly talk about the projects that we have been doing uh, in IUCAA. Okay, so we briefly talk about circumgalactic medium in one of the earlier slides. So it's the medium, gaseous medium surrounding in the immediate vicinity of galaxies. Let's take our Milky Way, which has a stellar mass of 10 to the power 10.7 solar mass, and halo mass of 10 to 12.3 solar mass, and virial radius of 280 kiloparsecs. And as you know, the size of the stellar disk for the Milky Way galaxy is only like about 15 kiloparsecs. So if you imagine that this is Milky Way, so then this is the part like only 15 kiloparsecs, central 15 kiloparsecs, you will be able to observe through stellar light. Okay, and that's we call galaxy in the usual notion. But galaxy doesn't end there, right? So you see the virial radius. Okay, that's basically scale. It's a scale or length scale uh, of the like collapsed medium, uh, collapsed region around this galaxy, which is for Milky Way galaxy is 280 kiloparsecs. So you can see that beyond 15, all the way up to 280 kiloparsecs, it's not empty, but it's filled with a diffuse gas that do not emit. And that's what we call circumgalactic medium. And if you do this calculation of volume, simply like 4 third pi r cube, where r is 15 kiloparsecs, and for CGM, if you take this virial radius, which is like 280 kiloparsecs, then you see that volume of the circumgalactic medium is 10 to the power 3 times. It's like 1,000 times more than the volume of the disk. So it's a lot of gas in there, okay, that are diffused, that we don't detect directly in emission. And you see that the galaxies, they cannot evolve in isolation. Okay, they will have to accrete gas from the intergalactic medium, and then there are this burst of star formation or supernova, which will basically eject metal rich gas in its surroundings. So lots of processes actually happening surrounding galaxies. And all of these processes are involved with diffuse gas that do not emit much. So if we want to understand these processes, we must probe this region. So that's what actually my main sort of focus or my research interest, which is also aligned with some other professors at IUCAA. So okay, I'll just say, okay, so importance of CGM study. Maybe I can just briefly tell you that why do we care about the circumgalactic medium? So as I just described, that galaxy is not only dark matter and stars and ISM, but it's the circumgalactic medium is an important part of the galaxy's ecosystem. and it, and we need to understand this medium in order to understand how galaxies interact with their surroundings and how those interactions actually shape the evolution of the galaxy. Okay, for example, gas accretion or recycling process or outflow processes. So those processes, if we want to understand, then we'll have to probe the diffuse gas around them. And the circumgalactic medium can account for the halo missing baryons and missing metals, which we didn't discuss. But if you remember in one of the earlier slides, that the galaxies, they contain 7% of the cosmic baryons, whereas meaning the stars in galaxies, whereas CGM is already contributing 4 or 5% of the cosmic baryons. So in terms of total baryons, the circumgalactic medium is actually close to the baryons that are within galaxies. So that's really important. And the CGM observables, for example, what is the equivalent weight or what is the column density you measure around in the circumgalactic medium of a particular type of galaxies, and how those measurements changes with let's say distance from the galaxies, we call profiles, for example equivalent weight profiles, column density profiles, etc. They can provide stringent constraint in galaxy evolution models. So we talked about simulations. So we can provide these observables to the simulators and sort of ask that under what conditions or what physical processes or what constraint you can sort of obtain in order to reproduce these measurements. Okay, so that's that. And I'll also skip these things. So again, the basic structure of this experimental setup we already discussed. Okay, so so you have a background quasar, and then there is this foreground galaxy. Foreground galaxy is absorbing your background light and producing absorption lines. So therefore, we actually analyze these absorption lines to understand what is happening inside this inside the halo of the galaxy. So it has two components. So you need a good quality quasar spectrum in which you will see the absorption lines, and then you will have to do a uniform galaxy survey. Okay, so unless you have the information about the foreground galaxy, you don't know which galaxy is causing this absorption, right? So you need to have uniform galaxy survey, and you also need to have very good quality quasar spectrum, background quasar spectrum, through which you will probe their diffuse halo. Okay, and so for that we have been using very powerful IFU's integral field spectrograph, which is called MUSE, installed in VLT. Okay, and we have two like surveys, one at high redshift and another is at low redshift. We call them MUSE Cubes CGM survey, and it stands for MUSE Quasar Field Blind Emitter Survey. Okay, so we have total 24 quasar fields uh, through which we observe like galaxies, like with MUSE, we observe galaxies around them. So these are white light image of MUSE. You can see at the center, you always see something very bright. So that's the background quasar. And then there are foreground galaxies, right? So we have both the components that are necessary for this kind of experiment. Now we have about 500 galaxies with well measured properties, and now we are trying sort of to understand the absorption lines produced by these galaxies in the spectrum, in the spectra of the background quasars. Okay, so that's the experiment we have been doing. So we have lots of state of the data to be analyzed and publish excellent science. And for that, we need young, motivated students like you. So I think I should just stop here. I had some slides which I wanted to discuss, but I think we are almost done. Yeah. So that's all. If you have any question, you can raise your hand and then unmute yourself. Okay.
Hello.
Yes, yes.
That the circumgalactic medium you're talking about, you told that they are consisting of baryon mass, isn't it?
Your voice is not clear. Can you try again?
Yeah. Am I clear now?
Yeah,
Hello.
it's better. Yeah.
Sir, in your talk, you talk about circumgalactic medium, which you told that they are consisting of baryon mass, mainly baryon mass. And the baryon mass, I can understand that they can be neutron and proton. And when I saw the absorption spectra you have shown, which is coming from the quasar and then passing through the cloud and giving us the absorption spectra, there you have shown that there are copper lines and other hard element lines. This thing was confusing to me. And one more thing I wanted to just ask you that can you just show us that how we can differentiate by that Doppler redshift you have talked about and that redshift you have talked about. So that redshift, when we are having a spectral line, and we know in the laboratory, in the red frame, we can see and analyze the spectrum lines and we can know that this is corresponding to this particular element. And when we are having it from the quasar, how do we know that those elements are there in the quasar and then we are getting redshift?
So your question is, how do we know that the lines are
Exactly corresponding to that element. I mean, because it's very difficult because after the
okay,
broadening,
okay. Yeah. So we have the whole list of rest frame wavelengths coming from all the transitions. And then there are facts like you will also have to consider the strength of the absorption line. If the oscillator strength is very low, okay, so then you will not be able to detect them. So that is also there. So we don't use the things blindfolded. We use some sort of uh, basic understanding about which transitions should be detected, okay, in the sense that let's say you are talking about some element which is really really rare, okay. So for example, the most abundant will be hydrogen, okay, and then next will be in terms of cosmic abundance will be oxygen and carbon and so on. So if you are talking about some very some element which is very rare, so then you can ignore their transitions basically. And also if the transition if the element is abundant, it doesn't necessarily mean that you will observe all of the transitions from that species, because again you will have to see uh, how strong the individual the transition of your targeted transition. So and also the rest frame wavelength. So since you are observing in a particular bandwidth, right? So let's say you are using optical band, okay? So then you have your lambda mean and lambda max of the spectrum, and you know what is the redshift of the background quasar, right? So with this constraint, you can also rule out some of the uh, transitions. For example, if the rest frame wavelength of some transition is very low, okay, in the sense like 700 angstrom or 800 angstrom, and your galaxy or your quasar is at redshift 1, then you can see that those transitions will not fall in the passband of your observation. So even with that, you can eliminate the possibilities of those transitions. So it's basically a never-ending process of this method of elimination. So you have to keep eliminating things and use some sort of your intuition about the way it should behave. Okay, any other question? One question in, okay. If the redshift is high, then what can we say about its recessional speed? Okay, you can calculate from your cosmology calculator how far, like what is the Hubble velocity it is. Yeah, that's a solved problem. You know how if you know the redshift, then you can calculate what should be the, or the delta redshift. You know that delta z by 1 plus z would be equal to delta v by c. So you can calculate what is the velocity at which uh, that object is moving away from you. Okay, anything else? If not, then probably I'll just stop here. Thank you all.
Thank you very much, Sowgat, for this lecture.